Hey guys, so in this video we're going to do a quick review of complex numbers. So that's really just when you have an expression that has a negative under square root, so that we use the imaginary number I to simplify. So last week you saw when you were solving quadratics that had a negative under square root, we said it didn't have any real solutions and didn't have any real x-intercepts. So we're still saying that. We're just now using this imaginary number I to be able to at least simplify these expressions a little bit more. So I have over here in the corner, I'm going to write the definition of I. So the definition of I is defined to be the square root of -1. So you would never have I under the square root because I really takes the place of a square root. Okay, so for example, when I have this over here, the square root of -36, what I do is, you don't always show all this work, but this is how I really get to my value in the end. So I can rewrite this as the square root of 36 times the square root of -1. That's how I can get to -36. And I break it up like that because then I know that the square root of 36 is a 6. And now this is exactly what the definition of I is. So that's how I end up getting 6i for the square root of -36. When you start doing these a lot, you don't ever really show all that work. You just know that, well, if we knew the square root of 36 was 6, then the square root of -36 is just 6i. So anything that has a negative under square root, we rewrite with I. So likewise, the square root of -48, what I could do is I know how to do this, square root of 48, so I know this is really just going to be, whatever that is going to have an I. But notice that I is not under the square root. It's replacing the negative part of the square root. So then if I do this, when I do this part, I end up getting 4 radical 3. So I really have 4 radical 3i. I tend to write it like this, 4i radical 3, only because then you can clearly see the I is not under the radical, where sometimes when people write it this way, which is not wrong, if you're kind of messy with that square root and can't tell where it ends, it's hard to know where the I is. So either one is fine, but I tend to go with the second one. Okay, so then we look at, I'm coming back up in this blue little bubble over here. I is the square root of -1. So if you took both sides of that and squared it, you would get the definition for I squared, which is -1. Okay, so what's kind of neat about that is I is imaginary. It's not on a real number system. But the second power of I, when you take I and you square it, you too get you're back to a real number. And every other power of I works that way. Okay, so let's look at now multiplying. Okay, so now if you know how to multiply 5 plus 2x and 3 minus x, then you know how to multiply these already. So it's not going to be to the last step that I'm even going to treat I as anything more. It's just a variable to me right now. Okay, so let's just multiply the same way we would. So I'm going to distribute out the 5 and the 2i. In other words, I'm FOILing. Okay, the same way I would because I'm multiplying two binomials. So I get a 15 minus 5i plus 6i minus 2i squared. So still, right now, I'm still just treating them like the same way I would an x or a y or any other variable. Okay, so then I'm going to combine these. Okay, so right now I have 15 plus 1i minus 2i squared. Okay, but so usually when you have just variables, you're done at this part because I don't have like terms. But I got to keep in the back of my head that we know this. We know this definition of I squared is -1. So if I can ever replace any power of I with a real number, I'm always going to do that. Okay, so what I'm going to do here is this part right here is -1. So that makes this 15 plus I. I have a -1 times a -2, so it becomes a +2. And I ended up really getting 17, which is the real part of this complex number, plus I. So it's not a coincidence that I got a binomial there. Every time I multiply out these two binomials, if they both have I, the part with the I squared ends up being part of my real number. So I have a real part and I have an imaginary part. So I won't get a trinomial for these, the same way I would if those i's were x's. So now let's look at one Example here that's very similar to the last one, except for the numbers that I chose to multiply out. So I want you to just think about, in the back of your head, I want you to think about if I were to do this. Okay, so if I were to multiply that, this is really just kind of in the back of our head what happens. And let's see if the same thing happens. So if I'm going to FOIL this out, I'm going to end up getting a 36. The outer gives me a minus 12i. The inner gives me a plus 12i. And then the last gives me a minus 4i squared. Okay, just like up here with this part up there, the outer and the inner drops out, cancels out to 0. Same thing happens here. Minus 12i and plus 12i. So that was going to be my imaginary part. Those were going to combine to my regular linear power of I. So I don't have that anymore. And now that we still remember that this part right here is negative 1, so I end up having 36. And this is going to end up becoming a plus 4, so I get a 40. Okay, so not only do all my i's drop out, but so I have an integer answer. Okay, I have one term. It doesn't have to be positive or negative. It can be either one, but it has no i's. It's a real number with no imaginary part. Okay, so we use that fact to get i's out of the denominator. Okay, just like we can't leave radicals in the denominator, we can't leave an I in the denominator either. So you'll see on this next slide, I have an example of let's try to rationalize the denominator. Okay, meaning getting the radical or an I out of the denominator. Okay, so I'm going to use that fact. I'm going to look at that 3 minus 2i. I'm going to say, well, how could I get rid of that in the denominator? What could I multiply by that makes that have no I? So then we think back to the last example that we just did, and we know that if we multiply it by what these are called conjugates, okay, when you've got the same binomial but different power, if I multiply it by that, just like we did in that last example, we know we're going to get rid of all the i's in the bottom, and that's our goal. Whatever I do to the bottom, I better do to the top, because really, by multiplying by this fraction right here, I'm really just multiplying by 1. Okay, it's the same process I do when I find a common denominator for something and change the denominator. So we've got to FOIL out both the top and the bottom. I'm going to do the bottom first to show you that the I does drop out. So if I do the bottom and I FOIL out, I have a 9, then I have a plus 6i, minus 6i, and then a minus 4i squared. Let me just finish with the bottom here. Okay, so the 6i's drop out, and that end really becomes 9 plus 4. I really have 9 plus 4 there. So my bottom is a 13. Okay, so my goal was to get rid of any i's in the denominator, and now I have a nice integer denominator. So let's go back and do the top. So let's see. I have a 6. My outer gives me a 4i. My inner gets me a 3i, and then plus 2i squared. Okay, so so these combine to 7i. And then the back now, 2i squared is really going to be a minus 2. Okay, because the I squared is a negative 1 times by positive 2 gets me a minus 2. So I end up with a 4 plus 7i, okay, all over 13. So there's multiple ways to write this. The first thing we want to look for is look at the 4, the 7, and the 13 and see if you can reduce by anything. But all those numbers I can't reduce by anything. So usually, this depends kind of on the textbook that you're using, but a lot of textbooks want to see this separated into 2 separate parts, meaning divide the 13 into the 4. Even though it doesn't go evenly, we write that part separately than this part. And the reason for that is because then you see the part separated by the 4 over 13 is the real part. The 7 over 13 is the imaginary part. So that's where we go. So we've got no more i's left in the denominator. And so this would be rationalizing the denominator the same way you would if there was a radical in the bottom. So hopefully those couple examples give you a quick little review for section I think this is 3.3. Okay, so good luck this week.